Normann. The next talk is going to be in English again. Philipp, from the same team as Timo is in, from Team Tesla, is going to talk about recommender systems again, but a different kind of recommender now. He's going to focus on transformer-based multimodal transformer based on text data and image data. No, but not from, okay. But anyway, okay, enjoy.
Okay, thanks. And hello, everybody here at OTTO and also joining us remotely today. You've heard about the latest advancements in our personalized recommendations from Timo before. And I'm happy to present to you another project that we've been working on recently. The talk is called Deep Multimodal Recommendations, Solving the Cold Start Problem. And I hope you will understand all of those words at the end of the talk. Short slide about me. I'm also a data scientist at OTTO, at the same team as Timo has explained. I think I won't go into detail. Here's the contact in case you want to ask questions at the end. I'll also show it again, don't worry. This is the structure. I'm going to explain the cold start problem, what it is and why it matters. Talk a bit about content-based recommendations, how we can use them to solve the problem, and then also talk about how this project actually started, because it was quite a coincidence. It started as a hackathon, and I'll talk a bit about that. And then we'll dive into the details of the model, the joint embedding model. And at the end, I'll draw a conclusion and hopefully give you some insights about our project. So, what is the cold start problem and why does it matter? As Timo mentioned, we often use interaction data from the shop to train our models. And it looks like this. There's a customer coming into our shop. He might want to buy one of those dresses. And then this creates an event that goes into our tracking data. And if he buys another dress after that, that also creates an event. And we can use these events to then train a model that predicts that those items are related to each other. And we can then use that to recommend them to other users who might like one of those dresses. That's all good, but what do we do if we don't have this data? So if this wasn't purchased at all, or not viewed, for example, then we don't have this tracking data, and we can also not train a model on it. And this is a problem, and this problem is called the cold start problem. So what do you do if you don't have this data? It mostly occurs for long-tail products. Long-tail products are products that are like really niche or well hidden in our shop. These are some obscure products that not many people have viewed or bought. And you can imagine that it's hard to predict something based on behavior for these kind of items. Another kind of product that is also affected by this problem is new products. So products that have recently been added to the shop also have very little or no data. And actually this problem is increasing for us as we are transitioning to a marketplace. More and more products are added to the shop every day. And right now it's about 2% of our products are younger than 1 week. So these are all the products affected by the problem. And that's why we wanted to solve it and deliver recommendations to the customers for these products as well. And the problem can only really be solved using content because we don't have behavior. So collaborative filtering is not an option. And now I'll show you some kinds of content-based recommendations that you could use. So we have text data. And for the text data, there are traditional approaches that you can use for similarity, like term frequency, just counting the words, how many occurrences does it have, and something more elaborate, like normalizing those. Those are like the classical approaches. And also you could use unsupervised learning, like LDA, or shallow learning like word2vec, where you get embeddings. It's like one layer neural network that learns embeddings for words or sentences. And you can use those to then calculate similarities. Recently, like in almost all fields, deep learning methods have also been the state of the art here. So transformers and RNNs before are becoming more and more relevant in this domain. And most state-of-the-art solutions use these. Image-based methods are originally, you could use something like attributes of an image, like the color, the histogram, shape, something really simple. But this doesn't really capture the meaning of an image. So if you want to know what's going on an image, this doesn't really help. And also deep learning has become a solution in this field, like CNNs, convolutional neural networks, are architecture you can use to process images. And there have been like really popular architectures published, like ResNet, that have been pre-trained on large corpuses of images, like ImageNet. And you can simply download those networks from the internet and use them to calculate vector representations of your images, which then can be used for similarity search afterwards. If you want to go a step further, you can fine-tune these CNNs, and you can use it to not classify on the image data classes, but for example, in our shop, we could train them to recognize categories from our shop. So you put a pants in, and it predicts that there's a pants on the image, and so on. If you have more time and more compute, you can also train these from scratch, which is usually not such a good option because fine-tuning them is always cheaper and more effective. Also, in images, transformers have become more relevant. There are vision transformers, and they're slowly starting to replace CNNs, but are still a little bit more complicated to train, and it might take some years before CNNs become obsolete. And now the question is, how do we bring those two together? That's called multimodal. So how do we use images and text in the same model? The goal is to bring these textual and visual embeddings into the same vector space. And you can there are multiple ways how we can do this. One is called embedding fusion, where you try to learn a projection, like you also train a neural network that maps from one space into another. So you try to map two pre-trained networks into the same vector space. Another way that you can do is joint embedding, so training in a model end-to-end that then produces textual and image embeddings in the same vector space by training the network. A popular approach from OpenAI as well is CLIP. This has been really successful also in classifying images, even though it hasn't even been trained on that task specifically. So when you use these feature extraction methods, you get vectors, and then you can use similarity measures to find similar products. Commonly used similarity measure is cosine distance. That's basically the angle between two vectors. You can also use like Euclidean distance. And when we're talking about sets, something you could use is like a Jacquard distance, like measuring the intersection between two sets. For example, if we count which words are occurring in an article description. So how did we actually come to solve this problem? It was actually much further on our roadmap due to its low. We thought it wouldn't have much impact. Basically, we thought this is like a niche topic, and we wouldn't be able to improve our economical KPIs much by working on this. And there was like an internal competition at OTTO that was actually trying to solve a different problem for procurement managers. So procurement managers are people that are like ordering the items, and they wanted to know how many units to order for a new item that hasn't been sold in our shop yet. And they wanted a model that could find a twin, like the most identical product in our shop that they could use as a proxy for forecasting the sales of a new product. And yeah, we participated in this hackathon, with two other teams. And this hackathon was over a period of 2 days. It was from different departments like business intelligence and CI, customer interactions. That's the department that's working on the web shop. There were 3 teams, 3 approaches. One was using a CLIP model actually by OpenAI, using an open source implementation of that and trying to train that on OTTO data. Second idea was using coming up with a baseline on existing models that we already had, which is always a good idea to establish a simple baseline before trying something complex. And the third option that we were working on was implementing a new model based on a paper that we found during the research phase in the preparation for the hackathon, which is actually published by Amazon Labs. And yeah, this is a paper, Joint Visual Textual Embedding for Multimodal Style Search. And as the title says, it's basically solving exactly the problem that we were trying to solve as well. So we thought it would be a good approach. And we also, after screening it, we thought it would be a viable option and we would be able to implement it in 2 days. So that's why we chose this. And the outcome of the hackathon was that, unfortunately, the first approach was not successful. They weren't able to train the model in the 2 days because the model is a huge, the clip model requires extremely large amounts of compute. And yeah, it was just simply not feasible in the 2 days to finish this. This might become viable in the future, but was unfortunately too complex for this approach. And yeah, the baseline succeeded. They were able to deliver results. But in the end, the team that hosted the hackathon chose the third option and adopted this as their new product, or as their approach to the new product, due to, first of all, better predictions. They were more happy with the results that it got comparing to the second to the baseline, and also it was not dependent on other teams. The second one was dependent on other teams delivering embeddings to the twins product, and this caused like dependencies and more complex operations in the future, and that's also why they made the choice to go with the third option. So let's have a look at what this joint embedding model actually does and how it learns these latent representations in the same space. Let's look at a simple example, like three products with text and images. I showed you ways how we could transform each of these images into vectors and also how we can transform text into vectors. So let's have a look at that. They are in different spaces. They're not related to each other yet. And if we look at them, we see that the boot is quite far away from the image of the boot, actually, and same goes for the other products. And the idea behind this joint embedding model is actually to minimize the matching pairs in this vector space. So you want to minimize the distance between the boot and the boot text and the boot image, and for the other products as well. So after training this model and optimizing this loss function, we come up with a vector space where matching pairs of text and image are close to each other. We can then simply add these vectors and calculate the distances between the resulting vectors. And this gives us a similarity metric that respects as well the image as the text. And yeah, vectors that are far away here are unsimilar, and vectors that are close to each other are similar. And we also use cosine distance here, although this looks like it's a Euclidean distance. That's just for visual representation. This is how the model architecture looks like. So we have a few components here. This is like the ResNet that I mentioned. This is a pre-trained ResNet also on ImageNet. And it's fine-tuned by fine-tuning the last layers using the loss functions that I will explain now. And the text embedding part is also very similar to Word2Vec. It's quite simple. It's just one layer. And we just sum up all these vectors for a sentence. And that gives us the vector representation of the text. Yeah, there's this loss. This is the MBMR loss, which stands for mini-batch match retrieval. And I will explain what that does in a second, but it's basically the moving the vectors closer to each other, what I just showed you. And we give it another block at the end to give it even more information in these image embeddings. We train a network that uses the image embedding to then predict which words occur in the text. So we have like a semi-supervised approach here. We use the text from the article that we know matches the image, and we train a network to extract these words again from the image. And this gives us a very rich representation here in this vector, which includes all of this information. Yeah, the hackathon had the goal of PBK classification, which is like product-based classes for our shop. This was the proxy metric that they wanted to use to determine a winner. So we also attached another classification head at the end and trained a model that also does that task. And this also gives you a bit more information here, but we noticed that it doesn't really make a lot of difference because the words already include a lot of more information than the PBK And the vocabulary is also much smaller. Yeah, these are the loss function for the mini batch retrieval for the math nerds out of you. So this is like the cosine distance up here and of the image and text pair. And we're trying to basically optimize the distance of the text and image embeddings and also image to text. So in both directions, you can imagine also this is like a matrix where the diagonal is the matching pairs. We're trying to maximize the scores along this diagonal. And we're doing that in both directions. That's what both of these terms mean. And this is like similar to a cross-entropy loss right down here, maximizing the probability of the matching pair to be close to each other. Yeah. Here's the attribute extraction part. This is quite straightforward. It's a multi-label classification task where we use sigmoid and cross-entropy loss again. The category extraction is also quite straightforward. It's a single label task, so we use softmax instead of sigmoid. And this is just a basic cross-entropy loss. Maybe let's talk a little bit about the tech stack now. So we're running all of this in the AWS cloud and use a couple of AWS services. AWS Batch, for example, is used for provisioning and running all of these jobs. So this helps us, basically, we just give it a Docker file, say on which kind of machine we want to run it on, and then AWS handles the rest. We don't have to provision these servers ourselves. EC2 for running highly available servers for all of the API endpoints. So when the front-end team asks us what to recommend, these services are running on EC2. S3, like one of the oldest and most popular storage services of AWS, we use that for storing the training data and model artifacts as well. And originally, we also used S3 for storing the images, but noticed that that was way too slow, actually, for training directly from S3. So it was 10 or 20 times slower than training locally, because you have to make requests to S3 each time you want to load an image. And this has to go over the network, and that's really slow. So we attach an SSD EBS device, load all of the images on there, and then train from there directly. And this achieved almost as fast training times as locally then. Some open source frameworks that we use are Apache Airflow. We use that for batch workflow management, so you can define which jobs should run after another. And Airflow also monitors these jobs and triggers them at specific intervals. Something else we use is ONNX. This is really useful for us. We use it as an exchange format for our models. So when we export a model from Python, for example, and want to use it in another language, you use ONNX as this exchange format, and you can use it in almost any language you want. And it also optimizes the model while it's exporting it, so it's overall a win for us. And recently, we've also started to use MLflow. We previously used TensorBoard for this, but MLflow allows us to compare these experiments that we do offline much better. So we also have the parameters that we use there, and it's basically automatic documentation for us of all the experiments we do. And it really helps us in our prototyping. Something we can also recommend to you is like Lightning AI. It has been recently renamed. It was called PyTorch Lightning before. And it's a high-level PyTorch framework similar to Keras, if you know it. It just gives you a lot of, it takes away a lot of your boilerplate code and prevents bugs that you could prevent easily, and it saves you time. So you should definitely use it if you use PyTorch. How does the model pipeline look? So I told you we're using product data to make these recommendations. So we also need to get the images for these products. We download them from an image server, like an asset server from OTTO, and tokenize all of the texts. So we split the texts, the words, and we clean up irrelevant words out of this to get a smaller vocabulary. We then train our model that I just explained. We get the ONNX model, and then we use it to create a scan index. A scan index is a nearest neighbor index that we can use for querying and finding nearest neighbors really efficiently instead of brute forcing this all the time. Using the scan index, we can then calculate top K recommendations and deliver this to the web shop. Where do you actually see this? It's on the product detail page. At the bottom, there's the carousel that shows you the similar articles. And usually we fill these with user behavior-based models because they perform better than using content-based recommendations here. And cold start model is only used to fill up the spaces that are remaining. But as I told you, there are also some products where this makes up all of the spaces because we don't have any behavioral data, and we have to use it to make all the recommendations. There was actually a model that was in production previously. It was a TF-IDF model, only using texts. And we were interested in seeing how this new model that we came up in the hackathon would compare against this. So we did an A/B test, splitting the traffic into 2 groups for 2 weeks and comparing those 2 models. After first visual inspection, we noticed that indeed our new model looked to be to deliver much better predictions, as you can see, and we were quite hopeful for the experiment. But these expectations were exceeded. So usually we see like single-digit improvements in these KPIs. As Timo showed you, we are very happy to see like 4% CTR improvement on the storefront or something like that. And double digits are almost never seen. And when we analyzed the results for the experiment, our analysts were very happy, and we could show them that there was a significant positive impact in the control group. 250%. We were really happy about that. And actually, we were also able to positively impact other, like the interaction with recommendations in overall on the product detail page. This is what you can see here. We were increasing clicks on the recommendations overall, and sometimes you can see like this cannibalization effect where one feature improves and the other feature degrades, but this didn't happen here. We didn't see, this is not a significant negative impact on other features, so it's an overall net positive on the recommendations for us. And actually, this was also very unexpected for us. It also improved economical KPIs for the whole group. So this is revenue in the whole group with the new cold start recommendations versus the old ones. And yeah, you can imagine that this is quite relevant for an e-commerce retailer. Yeah, thanks. Now we have the conclusions. What did we learn? Read more papers. So comparing your production systems to like the current state of the art can show you substantial opportunities for improvement, and it's always worth staying up to date. That infrastructure is important. We underestimated the amount of time that we would have to spend bringing all of this training infrastructure into the cloud. So actually making sure that these images were fast enough, and it's 80 gigabytes of data that we have to train on, and this was quite a challenge to get that to work. And so just to give you an idea, like it took us 2 days to train the model locally, or to implement the model and train it locally, and 2 months almost to bring it to production in the cloud. So this is like the time frames that we're talking about here. Do more hackathons. They're like a fun way for developers to try out new things, but it's also a valuable tool for product development, as we have seen. And it can come with pleasant surprises like this one. Complicated is not always better. This is like referring to the clip model. Maybe we would want to use something like that in the future, but starting off with something simple is always a better idea. And also go live as soon as possible, even if that's on a Friday afternoon. So yeah, thanks. And now we have some time for questions, I hope.
Thanks, Philipp, for the great talk.
You're welcome.
I'm kind of impressed that we don't have any questions yet from the audience. I would like to remind you that it would be great if you post your questions during the talk using the QR code, but maybe nobody has done this yet, but maybe nevertheless there are some questions now that would arise from the audience.
Yeah.
Kostas.
Yeah. Basically, that's So to repeat the question, why did we use like the simple word embeddings and not a transformer? It was in the reference paper that we tried to re-implement. They simply used this bag of words and showed that the results were quite promising. And there was also the other group that was already doing a textual transformer, like the clip model that is actually a textual transformer. So it would have been kind of, yeah, the duplicate idea in the same hackathon. And there was another question there, I think. Christian?
How many other possibilities are there to solve the cold start problem? But that's keep it short, and that's a very longer question. But how do you actually, because you said you also integrated not only new products, but also other products where you didn't have click data for. Is that correct?
Yeah.
Now this could be that the customer is telling us these are the so-called Ladenhüter. So you can have products which are in our store, and we have many of them. Probably don't want to. Yeah, no, of course, the only popular products around. But there may be
well, at least some, yeah, might be. Yeah.
You know, the crazy LED tree that you showed.
Yeah.
People don't want, and you're recommending it. So do you differentiate between what you're attaching as sort of what you're bringing in? Or are you saying, okay, I don't have data, so I just bring it in? Or are there probably products where we don't have data and we don't want them to recommend them very highly?
Okay, so yeah, let's start with that question first, maybe. So we would still, so these so-called Ladenhüter, these unpopular products that nobody wants to buy, basically, or wants to see, we wouldn't recommend them on other products because we have behavior data that shows us what people actually want. But actually, there's also like products that are just hidden, very well hidden in the shop, hidden gems, so to say, and there's also some feedback loops in the shop that prevent these items from being shown to the customer, actually. And these cold start algorithms bring them up, and we have seen that in the long tail, they're actually really engaging products that people want to see. So for example, if something's on the last search result page, people don't click on it, we don't train our models on it, we don't recommend it to people. So this is something like how a product can be hidden forever. Yeah, so the cold start is still like a fallback, and that's why we usually don't show these bad products. And the second question, as far as I know, there's only content-based approaches to solving the cold start problem. There's obviously more types of content you could use. So you could also use like graph-based approaches, for example, where you try to analyze relationships between products. Or we just use the product name and image now. And there's a lot of more product data that you could use to improve these cold start recommendations as well.
Okay, then we do have time for another question. By now, there's another one from the audience, and this would be, where would you use images or only text? Loudspeakers look the same. Boots and sandals can be visually distinguished to add value.
So why do we use text additionally to images? Is that the question?
I guess the question is, where would you use images or text only?
Oh, we don't. So we always use both.
Yeah. Okay.
Because
simple answer.
Yeah, it's sometimes if it doesn't help. So if it has the same information, those vectors would point in exactly the same direction. So it doesn't add any value. But most of the times there is some additional information in the text, so it helps.
Okay, thanks again, Philipp, for the great talk and for the great questions.